Good day to each and everyone, especially to Mom Nancy. Today, we will tackle all about the discrete mathematics for IT. So, discrete mathematics for IT has a one lesson that has a four topic. So, let's dig in. The first topic that we will discuss is all about the sets and relations. So, what is sets nga ba? Tara! So, set is a set of collections of distinct and well-defined objects, which can be anything from numbers, letters, or even other sets. Sets are fundamental in mathematics and are denoted by curly braces or braces. So, example of a set is let A is equal to 1, 2, 3, 4, 5, and let B is equal to banana, apple, and guava, and let C is example of red, yellow, and white. So these are example of a set. So let mark or remind that set is uses a denoted braces or denoted curly braces. So that is a set is the basic sets and operations. Basic sets and operations has a three parts. First is the union, second is the intersection, and third is a complement. What is union? So the union of two sets A and B defined as A union of B is a new set that contains all elements that are either set A or set B or both. Example, let A is equal to 2, 4, 6, and let B is equal to 8, 10, 12. So the set A union of B is equal to 2, 4, 6, 8, 10, 12. So that is the example of union. When we say union, if set A and set B is combined together, that is called union. Next is the intersection. So what is intersection? The intersection of two set A and B, denoted as A intersection of B, is a new set that contains all elements that are common to both set A and set B. So example, let A is equal to red, yellow, and white, and let B is equal to green, pink, and white. So what is the common in set A and set B? So only white. So white is the intersection of set A and B. So why white? Because white only is the common in set A and set B. So intersection says that are common elements in both set A and set B is called intersection. That's why white is intersection. Third part is the complement. Complement of a set A, denoted as A. Complement is the set of all elements that are not in set A, but are in the universal, the sets that contain all possible elements under considerations. Example, let the universal set U is the big set that contains all the elements is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So in set A, this is only a subset that contains sum of elements from universal set U. So it is 1, 3, 5, 7, and 9. So the complement of A is all the elements in the universal set but not in A. So look at and remove everything that belongs to A. Remove because those are in A. Those belongs to A. Therefore, the complement A is equal to 2, 4, 6, 8, 10. In other words, the complement of a set is basically the opposite group of elements. Everything not in the set but still inside the universal set. Next is the three types of relations. So first is the reflexive relation. So what is reflexive relation? A relation R on a set A is reflexive if every element in A is related to itself. Example, that A is equal to 1, 2, 3, and R is equal to 1, 1, 2, 2, and 3, 3. Why? So each element of has a pair with itself, just like in R is equal to 1, 1, 2, 2, and 3, 3. That makes reflexive. The extra pair doesn't affect reflexivity like 1, 2. It's just an additional relation. So that is the example of reflexive relation. Next is the symmetric relation. A relation R in set A is a symmetric if for every A or B in R, there exists B or A in R. Example, the relation is a sibling of. If Alex is a sibling of Bella, then automatically Bella is a sibling of Alex. Why? So this works both ways. So the relation is symmetric. In set notation, if our set of people is equal to Alex and Bella, because both ordered pairs are present, the relation satisfies the symmetry property. So that is the reflexive relation. Third one is the transitive relation. A relation R on a set A is transitive if for every A or B and B or C in R, there exists A or C in R. Example, R is equal to lives in the same city as. If Alice in the same city as Bob and Bob lives in the same city as Charlie, then Alice lives in the same city as Charlie. First, Alice lives in the same city as Babs. Second, Babs lives in the same city as Charlie. Since both of those are true, it automatically means that Alice and Charlie also live in the same city. So when the two connections line up, the first and the last are also connected. So it is a transitive relation because if a person A shares a city with person B, a person B shares a city with person C, then a person A also shares a city with person C. The second topic is all about the logic and propositional calculus. Propositional logic and its components. So it is known as essential logic or propositional calculus. And also, it is a branch of logic that deals with the relationship between the propositions statement using logical operators. It aims to analyze the logical relationship between these propositions without considering the internal structure or meaning. We have two components of propositional logic. First is the propositions. These are the basic declarative statements that can be true or false. Propositions are represented by variables such as P, Q, R, and others. Second is the logical connectives. These are operators used to combine or manipulate propositions. So logical connectives has five parts. So the first part of logical connectives is the NOT. NOT represent negation, it changes the truth value of proposition. The word not changes a statement to its opposite meaning. For example, it is not sunny. If the day is sunny, then the sentence is false. But if the day is not sunny, then the sentence is true. Second one is and. And represent conjunction. It is true when both propositions are true. The word and connect two statements and says that both must be true together. For example, it is raining and it is cold. The whole sentence is only true when it is really raining and really cold at the same time. The third one is or. Represent disjunction. It is true when at least one of the proposition is true. The word or connect two statements and means that at least one of them is true. For example, I will eat pizza or pasta. This sentence is true if I eat pizza or if I eat pasta. Or if I eat both, it becomes false because only if I eat neither pizza or nor pasta. Next is implies. Represent implication. It is true unless the antecedent left-hand side it is true and the consequent right-hand side is false. The implies shows a conditions and a result. For example, if it rains, then the ground will be wet. So the sentence is false only when actually rains but the ground is not wet. In every other case, it is true. So the last one is if and only if, represented by conditional. It is true when both propositions have the same truth value. The if and only if means that the two statements must be matched each together exactly. Either both are true or both are false. For example, you can enter if and only if you have a ticket. So the sentence if true if you have a ticket and you enter. Or if you don't have a ticket and you don't enter, it is false. If you have a ticket but cannot enter, or if you don't have a ticket but still enter. So the sentence is true if you have a ticket and you enter, or if you don't have a ticket but you don't enter. So it is false if you have a ticket but cannot enter. or if you don't have a ticket but still enter. So it is false. Next is the propositional logic that is used to represent and analyze binary operation. So, binary operation can be represented using propositional logic by associating logical propositions with operands and using appropriate logical connectives to represent operations behavior. And logical connectives depends on the nature of the binary operations. So, these can be represented using propositional logic. Next is the logical and conjunction. So the binary operation that is used is AND, A and B. Propositional logic representation A and B are proposition representing the operands. Use the logical connectives A or AND to represent the operation. A and B is true if both A and B are true. Example, let A is equal to I will study tonight and let B is equal to I will pass the exam. So the conjunction is A and B is equal to I will study tonight and I will pass the exam. So the logical and or conjunction requires both statements to be true, even if one is false, but the whole statement become false. So let A is I will study tonight and let B pass the exam. So number one, if I study tonight and pass the exam, so the whole statement is become true. So number two is if I study tonight but I don't pass the exam, so the whole statement is false. The role of logical conjunction is requires both statements to be true. But even if one is false, then the whole statement is become false. Next is the logical or disjunction. The binary operation that is used is or A or B. So example, let A is equals to I will go to the park and let B is equal to I will play video games. So the disjunction is I will go to the park or I will play video games. So let A is equal to I will go to the park and let B is equal to I will play video games. So if I go to the park and I play video games, so the statement is true because or allows both. So if I go to the park but I do not play video games, so the statement is true because one part is true. So if I do not go to the park but I play video games, so the statement is true because one part is true. So it means if the logical disjunction, if a statement is true, at least one part is true. If it false, only both parts are false. Third one is the exclusive or XOR. Binary operation that is used is XOR A, XOR B. So example, that A is equal to I will play football and let B is equal to I will play basketball. Then the A XOR B is equals to I will play football or basketball but not both. So if I will play football, then it is true. But if I will play basketball, then it is true. So the A, X, or B, the answer is false because you join the both team. The next is example. If you join the football, then it is true. But you didn't join the basketball, then it is false. So the A, X, or B is true because the role of exclusive is you can join football or basketball but not the both. So, exclusive or means a statement is true only when exactly one part is true. So, it is false when both parts are the same, both true or both false. Number 4 is implication. The binary operation that is used is implies A and implies B. So, use the logical connective implies to represent the operation A implies B. It is true unless A is true and B is false. Example, in school, let A is equal to I will study hard and let B is I will pass the exam. So A implies B is equals to if I study hard then I will pass the exam. So let A I will study hard and let B I will pass the exam. So if I study and pass the exam then it is true. But if I study and fail the exam then it is false because it is contradiction. But if I didn't study and didn't pass the exam, the statement is not broken. So, an implication is like a promise. It only fails when the conditions happen, but the result does not. Last one is the equivalence. The binary operation that is used is equivalent to A is equivalent to B. So, use the logical connective if and only if to represent the operation. A is if and only if is true if A and B have the same truth value. Example, I will go to the party and let B, my best friend, will go to the party. So A is if and only if B is equals I will go to the party if and only if my best friend goes. In example 1, if I will go to the party and my best friend goes, then it is true. In example 2, if my best friend go to the party, then it is true. If I didn't go to the party, then it is false. Then the answer is false because it's different. So equivalence means both statement always match, either both are true or both are false. So the rule is it is true when A and B have the same truth values, both true or both false. It is false when A and B are different. Third topic is all about the proof techniques. So proof techniques has four parts. Our first proof techniques is all about direct proof. So direct proof is a straightforward method where you start with the given premises and logically deduce the conclusion using a series of valid logical steps. Example, in statement, if a number is odd, then its square is odd. Let the number be an odd number, then its square is which is odd, so the square of an odd number is always odd. Next is the proof by contradiction. So proof by contradiction involves assuming the opposite of what you want to prove and then deriving a logical contradiction from those assumptions. So example, suppose there is a smallest positive number, call it r. Then construct a smaller one, consider r over 2 is positive and r over 2 is less than r. So we will found a smaller positive rational number than r, which contradicts the assumption that r was the smallest. Therefore, there is no smallest positive rational number. Next is the proof by contrapositive. So, proof by contrapositive is a technique where you prove a statement by considering the contrapositive, which is the negation of the conclusion followed by the negation of the hypothesis. So, a contrapositive just means we flip and negate the statement. Example, original statement using the implication. If it is raining, then the ground is wet. So, symbolically, where it is raining and the ground is wet. So, the contrapositive, if the ground is not wet, then it is not raining. Symbolically, the contrapositive always has the same truth value as the original statement. They're logically equivalent. So the last one is the mathematical induction, used to prove statements that are true for all natural numbers. There are two steps in mathematical induction, the base case and the inductive step. In the base case, you prove that the statement holds for the smallest value, often 0 or 1. In the inductive step, you assume that the statement is true for some arbitrary value n, and then show that it must be also be true for n or 1. So this process a chain of implications that prove the statement for all natural numbers. Imagine you are setting up dominoes in a line. If the first domino falls, then that is the base case. And whenever one domino falls, it knocks over the next, it is the induction step. Then all the dominoes will eventually fall. So this is exactly how mathematical induction works. Prove the first case, then prove if it works for one, it works for the next. So the next is the topic 4, which is the counting and combinations. First rule is the multiplication rule. So the multiplication rule is a fundamental concept in probability and combinatorics. It tells us how to find probability of two events happening together, or the number of outcomes when making multiplication choices. Example, choosing a password. Suppose you need to create a password for an online account, and the password must consist of 3 characters, one uppercase letter, followed by lowercase letter, and then 1 digit. So how many different passwords can you create using this criteria? So the solution is there are 3 strategies to creating the password. So choosing the uppercase letter, choosing the lowercase letter, and choosing the 1 digit. So first is choosing an uppercase letter. There are 26 uppercase letters in the English alphabet. So second step is choosing a lowercase letter. There are 26 lowercase letters in the English alphabet. third step is choosing a digit. There are 10 digits. So now, according to the multiplication rule, the total number of a password option is the product of the choices at each stage. So the total option, number of choices of uppercase letter times the number of choices for the lowercase letter times the number of choices for digits. So the total options is 26 times 26 times 10 is equal to 6,760. So you can create 6,760 different passwords following the given criteria. So in the example, the multiplication rule was applied to find the total number of outcomes when choices are made in multiple stages. So each stage's choices are independent of the others, and the multiplication rule helps us to find combined number of possibilities. So the next rule is the addition rule. So addition rule in probability, sometimes called the sum rule, tells us how to find probability that at least one or two events happens. So example, ice cream choices, you're at an ice cream shop and you're allowed to choose either a single scoop or a double scoop of ice cream. So additionally, you can choose 6 different flavors. So how many different combination of ice cream orders can you make? So the solution is there are two choices to consider, the number of scope and the flavor. So first is choosing the number of scopes. You can either choose a single scope or double scope. This give you two choices. So number two is choosing the flavor. So there are 6 different ice cream flavors available. So according to additional rule, the total number of different combination is the sum of the choices at each state. So the total combinations equals the number of choices for scope plus the number of choices for flavors. So 2 plus 6 is equals to 8. So you can make 8 different combinations of ice cream orders. So in the example, the addition rule was applied to find the total number of outcomes when choices are mutually exclusive, so you can choose both single and double scope simultaneously, and you're selecting one option from each of the given sets of choices. Next rule is the permutation rule. So a permutation is an arrangement of objects in specific order. Order matters in permutations. Compare with combinations where order does not matter. Example, arranging books on shelf. You have a collection of 4 different books that you want to arrange on a shelf. In how many different orders can you arrange this book? The solution is to solve this problem using permutations. We'll use the formula of permutation 1 where n is the total number of objects or books and r is the number of objects being arranged or books that being placed on the shelf. So in this case, n is equals to 4 since you have 4 books and r is equals to 4 since you're arranging all 4 books. Plugging these values into the formula, permutation of n is equals to 4 and 4 is equals to 4 factorial over 4 minus 4 factorial equals 4 factorial over 0 factorial is equals to 4 times 3 times 2 times 1 over 1 is equals to 24. So there are 24 different orders in which you can arrange the books on the shelf. So this makes intuitive since because for the first book you have 4 choices and second book remaining is 3 books. You have 3 choices in third book. So the remaining 2 books is you have 2 choices and the last book remaining is the 1. So you have 1 choice. So the total of arrangement is 4 times 3 times 2 times 1 is equals to 24, which matches the result we obtained using the permutation formula. The next rule is the combination rule. Combination is a selection of objects without regard to order. Order does not matter, unlike permutations. Think of it as choosing a group in not arranging them. Example, selecting a committee. You are a part of a club with 7 members and you need to form a committee of 3 members to plan an upcoming event. So how many different ways can you select this committee? So the solution. So to solve this problem, using combinations, we will use the formula of combination of n, taking r at the time is equals to n factorial over r factorial times n minus r factorial, when n is the total number of objects or club members and r is the number of objects being chosen or the committee members. In this case, n is equals to 7 since there are 7 club members and r is equals to 3 since you're selecting a committee of 3 members. So plugging these values into formula,
combination of n taking r at a time is equals to n factorial over r factorial times n minus r factorial. So the combination is 7 and 3 is equal to 7 factorial over 3 factorial times 7 minus 3 factorials equals to 7 factorial over 3 factorial minus 4 is equals to 7 times 6 times 5 over 3 times 2 times 1 is equals to 35. So there are 35 different ways to select a committee of 3 members form a group of 7 club members. In these examples, combinations are used to find the number of ways to select a group objects or members from a largest set without considering the order in which they are selected. So the result is the total number of unique combinations for forming the committee. So next is the application of combinatorics in cryptography. So what is cryptography? So it involves techniques for secure communication and data protections. So combinatorial concepts are used to design encryption schemes and use and ensure the security of message. Next is the permutation and substitution. Substitution ciphers involve replacing letters with other letters or symbols. Combinatorics is used to calculate the number of possible cases and the resulting number of possible encrypted message. Next is the combinatorial analysis of attacks. Cryptanalysts analyze patterns in encrypted message, and combinatorial methods help estimate the number of possible cases, allowing them to focus on feasible attacks. The other one is the permutation-based ciphers. Block ciphers such as advanced encryption standard involve permutation of data blocks. Combinatorial techniques are used to design and analyze the efficiency and security of these ciphers. The next one is the coding theory, deals with the error detection and correction in digital communication and storage system. The other one is the combinatorics is essential for designing error or correcting codes. Next is the error correcting codes. Combinatorial methods help us design codes that can detect and correct errors introduced during data transmissions or storage. For example, Hamming codes and Reed-Solomon codes rely on combinatorial properties for their effectiveness. The next is the Hamming distance. Combinatorics help analyze the Hamming distance between code words, which determines error detection and error correction capabilities of codes. The other one is the combinatorial optimization in decoding. Combinatorial optimization techniques are applied to efficiently decode, receive code words, and correct errors. Next one is the probability theory, deals with uncertainty and randomness. So the combinatorics is fundamental for calculating probabilities and understanding the outcomes of random events. Counting methods, combinatorial counting methods such as permutations and combinations, are used to calculate probabilities of different events in various probability problems. Next one is the sampling and probability distribution. In problems involving sampling and probability distributions, combinatorial methods are employed to calculate the number of ways event. The last one is the binomial and multinomial distributions. Combination coefficients appears in formulas for calculating probabilities, multinomial distributions, which model the outcomes of repeated independent trials.
So that's all the topics for lesson 1. Thank you.